So this is the Keel software. Open a new project. So give some project name. We are going to work with timers now. So I have given project name as timers. And the target is Atmel 89C51. Any 51 based microcontroller. You can select the target, click on OK. And now choose whether to add the startup file or not. So we'll initially start with assembly language program. Then you can click on no here. No startup file is required for assembly. So now take a new file, start writing the code. Okay. So we are now doing experiment 3, which is timer operations, timer programming. In this, we'll see 3 programs. One is write a program to generate a square wave of frequency 100 Hz using timer 0 in mode 1 of operation. 100 Hz on, we'll take some pin, maybe port 2.5 using timer 0 on mode using mode 1 of operation. This is our first program. The second program, same, write a program to generate a rectangular wave of 100 Hz frequency with 30% duty cycle on timer 1 for a change in mode 1 of operation. There's the second one. And the third program, write a program to generate 5 kilohertz square wave of square wave on P1.0, and let this be on P1.7. You can take any port pin except port 0, because port 0 doesn't have pull-ups. During simulations, it may not work. Either port 1, port 2, port 3, anything you can take. On port 5 kilohertz square wave on P1.2, let us use now timer 0 in mode 2 of operation. So we'll explore the mode 2 also. Okay. So these are the programs we are going to see today. So come to the first program, 100 Hz frequency on P2.5. Okay. So the frequency is 100 Hz waveform and it is a square wave. So for square wave, on time and off time are same. On time and off time are same, right? So if the frequency is 100 Hz, Then what is the time period? Time period is 1 by 100 Hz. How much is this? 0.01 second, or else I can take this as 10 millisecond, right? Okay. So the time period of a square wave that we are going to generate is 10 millisecond. As it is a square wave, on time and off time both are same. So we are expecting that as 5 millisecond. So as per the given specifications, I have to complement P2.5 for every 5 millisecond. Okay. So that is the action that we have to do using 8051, right? So from the given specification, the first step is to compute desired time delay. Okay. So we got that as now 5 millisecond. Okay. So once you, sometimes they may give directly time delay, or else sometime like this, the frequency of the square wave they will give, from which you have to extract your time delay. Okay. So the desired time delay is a 5 millisecond. So the second step, compute the count needed to generate 5 millisecond amount of delay, that is TD, amount of delay. Okay. So how can we do this? As per the formula. The formula is depending on the mode of operation, as they have given mode 1 of operation. So the formula is FFFF minus initial count to be loaded in your registers plus 1, which is equal to your desired time delay into the crystal frequency, F oscillator frequency, divided by 12 is the formula, right? From which you can compute your IC. How can we got this formula? As you know, 8051 clock frequency is F oscillator or the crystal frequency that they have given. And 8051 timer frequency is F oscillator by 12, as timer circuit dividing the crystal frequency by 2. So F oscillator by 12 is the operating frequency for the timers of 8051. This means the timer registers will increment its count for every 1 clock period. Here the timer clock is F oscillator by 12. So this is nothing but for every 1 count, 1 clock pulse, for every 1 count, I am getting a delay of F1 by F timer clock, which is nothing but 1 by 12 divided by F oscillator. Okay, so which is equal to, based on the frequency that you are obtained, F oscillator, you compute for 1 count. For these many seconds, right? For a TD amount of delay, how many clock pulses you have to count, that you need to compute, which is equal to, that gives us N as, using the cross formula, TD into F oscillator by 12. So as the counters or the timers in 8051 are upcounting, so these are not the actual value to be loaded. Actual value to be loaded is F maximum count minus the initial count plus 1. Okay. So whatever you got number of clock pulses, that this is the initial count to be loaded in the register. So by equating these two, I will be getting the formula, this one. Okay. So after substituting the crystal frequency and the desired time delay in this formula, I will be getting the initial count as EE00 in hexadecimal. That we have done in theory already. You do calculations that how can we do so? If assuming the crystal, here one thing that we have to assume, the crystal frequency is 11.0592 megahertz for this default frequency of the crystal. So 11.0592 megahertz, right, into 10 power 6. This is the crystal frequency. This is actually divided by 12. This is the timer frequency, 921.6 kilohertz. So if I 1 by this much is the time period generated for one clock pulse, 1.085 microsecond. I want how much clock frequency? How many number of clock pulses for the desired count of TD? TD is 5 millisecond. So as per this formula, reverse this into 5 millisecond, 5 into 10 power minus 3 millisecond. It is 10 power minus 3. This should be, so which is nothing but 11.0592 divided by 12 into 5 into 1000. So these are the number of clock pulses which should be subtracted from 65536 minus 4608. So I got 6928. That is in hexadecimal. Decimal is 6928. In hexadecimal, it is EE00H. Okay. So like that, we will calculate the initial count to be loaded. This is loaded in your timer registers TL0 and TH0. Okay. So now the third step after computing initial count, first two are your computations. Next, configure TMOD register. That's the next step. So as TMOD register have the bits gate, C by T bar, M1, M0. For timer 1, first 4 bits. Next 4 bits for timer 0. Right? So as we are using only timer 0 for our operation, the first 4 bits will be 0. Gate software count 0. Timer mode C by T bar 0. And we want mode 1 of operation as we have taken 16-bit timer or counter M1, M0, mode 1 of operation. So with this, we will be getting a value of first 4 bits 0, next 4 bits 1. So 01H has to be loaded in TMOD register. Okay. So after this, what is the fourth step? Load initial count. And then fifth step, start the timer to run. And then wait for the flag. As we know, timer, whenever it has started, using how can we start the timer? Using timer run bit, TR0. And wait for the flag, TF0. Once the timer is started, it will start incrementing the count in the timer registers. As and when it has roll off, rolls from all ones to all zero, then the flag is set. Whenever the flag is set, it is clear that the timer has completed the counting. Then you can, once the flag is clear, it is clear that the desired time delay has been generated. After that, what you wanted to do, you want to complement the flag and output pin, right? So that you have to do. Complement the port pin and go back again to generate the same 5 millisecond delay. So you need to load the initial count again. So go back to step 4. So these are the steps to program. So accordingly, in assembly language, if I want to write in assembly, we'll start with 0, org 0. And as per here, the first two are computations. Third is your actual program. Tmod should be loaded with 01H. So the instruction move tmod comma 01H immediate addressing. And then you first clear P2 dot, which is what is the port pin you wherever you want to generate your square waveform. The pin is P2.5, right? P2.5. So make it first initially output by clearing the pin. Okay. So P2.5 configured as output. After this, load your initial count. Lower byte of count TL0 is loaded with 0 and TH0 with the value FEEH. Okay, only 2E. And then start the timer by using set bit. And now wait for the timer TF0 till it becomes 1. Jump on no bit. Okay, so if the bit is 0, you should wait. So I'm going to the same instruction. I'll be in the same instruction till the bit is 1. Once the bit is 1, you can come out here. So before that, what you want to do? You want to complement the port bin, complement P2.3. And then you have to go back to again loading the initial count, because once the count is completed, registers will be loaded with cleared with 0. So you have to load again the initial count to generate the same delay. That's why you have to go back. But before going back, you need to do clearing of a timer run bit as well as a timer flag bit. If you haven't cleared the flag bit, what happened? It doesn't allow the timers to count. Okay. Timer operation will be stopped until the flag is cleared. Okay. That's why you have to clear that and then go back by using schemp with a label. Again, my label should be here. Load the initial count. Okay. So this is a simple program, and finally end your code using the statement end. Okay. So save your file with extension maybe timer at 100H extension .am. ASM is mandatory. Now double click on source group, add your ASM file. Okay. So is this the file added? Yes, it is the file that was added. Now compile it. If you have any errors here, you will be getting no errors. Fine. Build it, and then what you have to do? Debug the code. For debugging, enter into debug session, clicking on here, evaluation mode fine. Click on OK. So we were entered into debug session. Okay. So now I'm going with the burst execution. So it is executing continuously. It won't stop because I have given S jump, right? S jump. Okay, short jump, a relative jump again continuously. So program will not end. The output, how can we observe? Because the outputs are peripherals, IO ports, port 1. Okay, you can check uh, what is the pin? P2.5, right? Not port 1. Peripheral is port 2. Okay, so P2.5 is updating continuously. Okay, so this is one way to check the output. We want as a waveform manner. So click on logic analyzer for observing the waveform. Set up the pin. Insert the pin P2.5. Click on enter. No, sorry. I actually, what's the mistake is, anybody have recognized the problem? You have configured port pin P2.5, but you have complementing P2.3. That's why two changes are happening. You need to complement P2.5 only. Save again, compile, build, go to debug session now. I have set up the pin, but it is in analog mode. Change it to bit mode, then close. Now run the pin. Okay. See, P2.5 is updated. It is updated. Now, how to measure the frequency of it? Stop the execution and click here. So this is my reference point mouse position. Okay. One is mouse position, another is reference point. That difference we need to measure. But we got it as 200 Hz around. But actually we are expecting 100 Hz only, no? Again, the issue here is the crystal that we are considered for operation is 11.0592 megahertz. Come out of debug session. That change of crystal you have to do using configuration tool. How can we go here? Click on here flash, configure flash tools, go to target tab, the device. Okay, target tab. Here, change the frequency 11.0592 megahertz. It is order megahertz. Click on OK. And then now debug it. Now run the code. You may get your correct output. Stop here and now measure the frequency. This is my reference point and this is my mouse position. Match here. Okay. So I'm getting 10 millisecond delta, which is 99.6. Even that small difference is here I am unable to map properly as the first reference point. Some small change due to my mouse. Okay. Otherwise, while we getting accurate delays using hardware timers. That's the advantage of timers. Okay. Right. We are going to end the meet in another 5 minutes. This is how you can observe the waveform. You take screenshots of this and paste it in your outputs as an outputs. Okay, that you can do. This is assembly. If I want to do the same thing in C, take a new file. In C, to write it in C, I have to start with register 51.h and I want a bit SFR bit, renaming that port pin P2.5 to be given as a cap 5 and then your main same statements which you have used here, that we are writing it as a high level statements. First is T mod. Registers have to be referred as capitals only. P, T mod. These have to be referred capital. That is one condition in C. And then my wave initially is 0, that configures it as output mode. Then load TL0 with a value 0. And then load TH0 with a value EE. And then TR0, we are making it set. And then now we are waiting for the flag. If the flag is 0, 0, we'll be in the while loop only. Here semicolon is mandatory. Once we got this, we will complement the wave. And then stop the timer. TR0 is equal to 0. TF0 is equal to 0. And you have to repeat. So I can use a while loop from here after loading initial count. You need to load initial count again to generate the same delay. Okay. So use while of 1. Okay. These statements we are. So this is the C code. So save this as extension C with extension .c. Okay. So now add this file to the group. Before adding that, remove the old ASM file. Remove the file. And now add the file, old present file. C source. This is ASM, sorry. I have to add C file. So add the C file. Okay. I have added even ASM, remove that. For working with C, I need a startup file, add that also. So startup is not there in my here. So what should I do? I have to close the project and create the new project because startup file I have not added earlier. So better to close this project and create a new project. Well, 89C51 target. So now add the startup here. Okay, so now startup is there. Add your C file, which we have added in the folder earlier. This is our C code. Okay, now remove the breakpoints. Now compile. There is an error. TF. There is TF. TF0, right? Not just TF. Okay, compile, build, and now execute. Before execute, what should I do? I need to change the clock because the project has changed. So the clock changed back to 24. Now change that to 11.0592 mega. Then click on OK. Now compile, build, rebuild all. Not required rebuild all, actually single main. Now go to debug. And run your code. So you can run your code. Same output you can observe. Timer. Port 2, right? Port 2 is blinking. And you can observe that in logic analyzer even by setting up the pin, which is P2.5. Close. Okay. So same output you can get. You can even measure on time and off time also. 5 millisecond. And this is 10 millisecond. Okay. So this is how you can observe the output. So one more thing that I can tell you using observing peripherals, your timer option is there. No, we have operated on timer 0. So see how the timer registers are modifying its count, its mode of operation, which we have configured in our programming that you can observe. For a small instant of time, timer run bit is clearing that we are unable to observe anyway. It is executing at order of microseconds. Okay. So this is how timers are working, both assembly and C. Okay, you can take screenshots of the program, but already programs were given in theory also. Okay, work out this. If you have any issues, we'll see in the next coming join. Okay, join again after 10 minutes. Before that, you try to execute this program, both assembly and C. Take a screenshot. Meeting is going to end. We'll join again after 10 minutes. Is there any doubts?